Morning students, myself Dr. Pawan Thapre, HOD of Electrical Engineering Department, SND College of Engineering, Yola. Today we will discuss the subject Power System 2, the unit number 6, the lecture number 5, layout and various part of HVDC transmission. Okay, so this is the schematic diagram of a typical HVDC converter system. It is the three-phase 50 Hz AC bus. It is given to the converter, means which converts this AC into the DC reactor is connected, and after that the DC line is transmitted. Okay. So these are the different parts of the HVDC transmission system. In that the pulse converter is there, DC reactor is there, DC power bus is there, DC surge capacitor, DC line arrestor is there, neutral bus is there, damping circuit is there. So these are the different part of the HVDC transmission line. It is the schematic diagram. So what are the various type parts of the HVDC system? First is the converter, second is the converter transformer, third is the smoothing reactor, fourth is the harmonics filter, fifth is the overhead lines, sixth is the reactive power source, and last is the earth electrode. So this is the part. So what is the function of converter? First part is the converter. The converter are the main part of the HVDC system. This usually consists of the two three-phase converter bridge connected in series to form 12 pulse converter unit. The total number of wall in such a unit are 12. The wall can be packed as a single wall, double wall, or quadri wall arrangement. Each wall is used to switch in a segment of an AC voltage waveform. The converter is fed converter transform connected in star-star or star-delta arrangement. The wall can be cooled by air, oil, water, or frozen. Liquid cooling using deionization water is more efficient and result in reduction of the station losses. This is the converter unit. In that circuit, we see that it is a three-phase AC bus, which is given to the star-star connected. And after that, this star and delta connection, secondary side of the transformer is the delta connected. It is given to the double wall, quadratic wall, or quadrilateral wall. So this is the total 12 wall is there, which converts this AC into the DC form. So AC supply is converted into the DC. Next, the rating of the wall group are limited more by the permissible short circuit current than steady state load requirement. The design of wall is based on the modular concept where each module contains a limited number of series connected thyristor levels. Wall firing and signals are generated in the converter control at the ground potential and are transmitted to each of the thyristor in the wall through a fiber optic light guide system. The light signal received at the thyristor level is converted to the electrical signal using gate drive amplifier with the pulse transfer. The walls are protected using scrubber circuit, protective firing, and gapless surge arrest. So this is the one table which shows the various types of rating of the comparison of the power semiconductor devices. So this is the maximum voltage rating, maximum current rating, voltage blocking, gating, conducting drop, switching frequency, development target, maximum voltage rating, development target of maximum current rating. This is shown by the thyristor, GTO, IGBT, SF thyristor, MCT, and MOSFET. Second part is the converter transformer. For 6 pulse converter, a conventional 3-phase or 3 single-phase transformer is used. However, for the 12 pulse configuration, following transformer are used. First, 6 single-phase 2 winding. Second, 3 single-phase 3 winding. And third is 2 3-phase 2 winding. In converter transformer, it is not possible to use winding close to yoke. since potential of its winding connection is determined by the conducting wall. Here, entire winding are complicated insulated as leakage flux of the converter transformer contain very high harmonic content. It produces greater eddy current loss and hot spot in the transformer type. In case of 12-pulse configuration, if two three-phase transformers are used, one will have star-star connection and other will have star-delta connection to give phase shift of 30 degrees. Since the fault current due to the fault across wall is predominated, controlled by the transformer impedance, the leakage impedance of the converter transformer is higher than the conventional transformer. On line tap charging, on line tap changing it used to control the voltage and the reactive power demand. Next part is the smoothing reactor. At its name, this reactor are used for smoothing the direct current output in the DC line. It also limits the rate of rise of fault current in the case of DC line short circuit. Normally, potential or total air core magnetically shield reactor are used. Disc coil type winding are used and brushed to withstand the short circuit current. The saturation inductance should be not be too low. Next part is the harmonic filter. Harmonics generated by the converter are of the order of the NP plus minus 1 in AC side and NP is the DC side, where P is the number of pulse and N is the integer. Filters are used to provide low impedance path to the ground for harmonics current. They are connected to the converter terminals so that the harmonic should not enter in the AC system. However, it is not possible to protect all harmonics from entering into the AC system. Magnitude of some harmonics are high and the filter are used for them only. These filters are used to provide some reactive power compensation at the terminal. Next part is the overhead lines. As monopolar transmission scheme is the most economical and the first consideration is to use ground as a return path for the DC current. But use of ground as a conductor is not permitted for the longer use. And a bipolar arrangement is used with the equal and opposite current in both poles. In case of failure in any pole, ground is used as a return path temporarily. The basic principle of design of DC overhead line is almost same as AC line design, such as configuration, tower, insulators, etc. The number of insulators and clearness are determined based on the DC voltage. The choice of conductor depends mainly on corona and field effect consideration. Next part is the reactive power source. As such converter does not consume reactive power, but due to the phase displacement of the current drawn by the converter and the voltage in the AC system, the reactive power requirement at the converter station is about 50 to 60% of the real power transfer, which is supplied by the filter, capacitor, and the synchronous condenser. Synchronous condenser are not only supplying reactive power, but also provide AC voltage for the natural commutation of the inverter. Due to the harmonics and the transient special design machine is used. Next part is the earth electrode. The earth resistivity of at upper layer is higher. It is 4000 ohm meter and electrode cannot be kept directly on the earth surface. The electrodes are buried into the earth where the resistivity is around 3 to 10 ohm meter to reduce transient overvoltage during the line fault and gives low DC electrical potential and potential gradient at the surface of the earth. The location of the earth electrode is also important due to the possible interference of the DC current ripple to the power lines, communication system of the telephone and railway signals, etc. Metallic corrosion of pipe, cable, shield, etc. Public safety. The electrode must have low resistance less than 0.1 ohm and buried up to the 500 meter into the earth. So thank you very much for the today's lecture. Thank you.